Ellipse Synthesis of a Five-bar Linkage by Mark Plechnik. Consider the finite position synthesis of a 1 degree of freedom mechanism. For example, we might specify 5 task positions and then solve for a planar 4-bar linkage which could move an end effector through those 5 task positions. In this paper, we look at something new. We look at the synthesis of multi-degree of freedom mechanisms. Our specifications come in the form of velocity ellipses. So for example, we'd want to solve for a 5-bar linkage, which could create various velocity ellipses at specified points in its workspace. To specify ellipses in the plane, let's consider the rotation of a coordinate frame. Or perhaps we can consider the reflection of a coordinate frame. Both cases apply, but let's just stick with the rotation for now. We could then take the circle associated with the coordinate frame and stretch it horizontally, stretch it vertically, defining horizontal and vertical semi-axis lengths, and then setting its orientation in the plane. These geometric parameters define a Jacobian which defines the mapping of a circle into an ellipse. The geometric parameters form the Jacobian through the singular value decomposition. We could specify several ellipses at various points in a workspace. Our goal is then to solve for a linkage, a 5-bar linkage, that can actually produce these velocity ellipsoids. Specifically, our design parameterization looks at the pivots of this 5-bar linkage in a home configuration. So our design variables, what we're actually solving for in blue here, are values for these 5 pivots, which define our 5-bar linkage, which should produce these velocity ellipses that are specified. Next, let's formulate the synthesis equations. On the right, we have pictured a 5-bar linkage in a reference configuration and a displaced configuration. There's 4 moving links. The angular displacement of those links is measured from the reference configuration by the angles phi, rho, psi, and theta. We form our constituent equations. We have the loop equation of the 5-bar linkage, and then another vector path which traces up to the end effector point. We introduce some extra notation to make the equations more compact, and then we take the derivative of the loop equations. The first derivative loop equation is rearranged into matrix form. The angular velocity rho dot is then substituted into the second derivative loop equation. This equation can then be factored out to form the Jacobian matrix. The 4 entries of the Jacobian are organized into 2 column vectors, J1 and J2. Our synthesis equations comprise of the loop position equations and the equations which define the Jacobian entries. Jacobian entries are defined through the geometric parameters describing specified ellipses through the singular value decomposition. We're going to consider 2-position synthesis. Since we're using a reference configuration parameterization of 5-bar linkages, at the first position, j equals 0, the angle displacements should all equal 0. Hence, for the position loop equations, we disregard j equals 0 as it will be an identity. Our unknown variables then are the 10 coordinates of the 5 unknown pivot locations in a reference configuration and 4 angle displacements in the second position, the j equals 1 position. That's 14 unknowns, but the number of equations we have is 12, So we go ahead and specify one of the fixed pivots, B0, yielding a square system of 12 unknowns and 12 equations. Let's begin solving our synthesis equations. Unknown pivot locations are indicated in blue, and then unknown angles are indicated in green. We begin by multiplying the two Jacobian entry vector equations by the negative of a 90-degree counterclockwise rotation. RCP can be solved in the bottom equation and substituted into the top equation, coming up with these two new vector equations. They can then be substituted themselves into the bottom loop equation, forming this new expression. This new expression introduces intermediate variables alpha and beta. Just looking at this expression here, we see that the only unknowns are the x and y coordinates of the unknown pivot A0 and the new alpha intermediate variables. They appear linearly in this expression, and so they could be solved for outright in these four equations. Since A0 is now known, this is indicated by colorizing it in black. However, we've introduced four new unknown variables, the beta intermediate variables. To continue on, we substitute the beta expressions into these two expressions formed from the Jacobian entry expressions, creating these two new expressions. From here, we could eliminate intermediate angles phi and rho by taking the magnitudes of both sides of the equations, forming a new system, a 6x6 subsystem in terms of the unknown components of Cx0, Cy0, and the beta intermediate variables. The beta variables can be eliminated by solving for each of them in these two expressions and then substituting the result into this expression, forming a new system. This new system is a 2x2 subsystem, with the only unknowns being the components of C0. We could eliminate the radicals in this expression and transform this into a polynomial equation. This polynomial system here, considering j equals 0, 1, is quadratic in terms of its unknowns, Cx0 and Cy0, meaning that there's four solutions of the pivot C0, which are all found numerically. Upon finding these four solutions, we back substitute into our beta expressions. However, it's unclear whether we should use the plus or minus signs in front of the radical expressions. We go ahead and check all 16 combinations, considering j equals 0, 1, of sign combinations, and testing each one against satisfying this expression. We always found that one of the 16 sign combinations yielded a valid solution. We take that solution, proceed forth, back substitute into this expression, and find unique values of phi and rho. At this point, we have four solutions for dyad ACP, but only two of these solutions had zero angles in the reference configuration. The solutions that did not have zero angles in the reference configuration indicate the same dyads but measured from some other reference, and hence they are discarded. We've exhausted the useful information in these three synthesis equations, so we discard these as well, and instead make use of our beta equations going forward in the synthesis solution process. We take our remaining loop equation and multiply it using the planar analog of the cross product by RDF. The resulting expression is manipulated and combined with the beta 2 expression in order to yield a geometric condition that the vector which spans across length df must be collinear with some vector delta, where delta is a fully evaluated vector. The vector which spans across length df could be written a number of ways, including rotated from the reference configuration or a length rotated from global horizontal. We take into account that offsets by pi will still satisfy the collinearity condition we desire, and we could solve for a number of values for theta hat. The theta hat values could then be transformed back to the reference configuration. We next define new gamma intermediate variables. The gamma variables are set up such that the beta intermediate variables can be written as their ratios. We see that gamma 1 is already fully known as is. Gamma 3 could be easily solved using the beta 1 expression, and gamma 2 can easily be solved using the beta 2 expression. Going forth, we'll use these gamma expressions in our synthesis equations. The gamma values are all fully known at this point. Looking at the gamma 2 equation, it's only unknown as f naught, and it appears linear in these two equations. Hence, f naught is now easy to solve for. We take our remaining loop equation and rearrange it, placing known terms in epsilon 1. The unknown angle psi 1 could be eliminated from this equation by taking the magnitude of both sides of the equation. We can then take j equals 0 of the gamma 3 equation and note that these two expressions are linear in the xy components of d naught. Hence, d naught is now easy to solve for. The remaining unknown is psi 1, and it is easy to solve for. We've now completely solved our synthesis equations. To recap, we found one unique value for A naught. We found 4 solutions for C naught, but only 2 were valid, yielding 2 solutions for dyad ACP. And then for each dyad ACP, we found 4 solutions for dyad BDF, but this includes 2 repeats each. So generically, we find 2 solutions for each dyad ACP, and then for each of those, we find 2 solutions for dyad BDF, yielding 4 5-bar solutions in total. The synthesis solution was applied to a few examples. For the first example, 2 ellipses were specified. The ellipse specifications are contained in this table, and the 4 synthesis solutions are contained in this table. The synthesis solutions are visualized here. We see that the first solution was able to transition between the 2 specified ellipses without any problems. The second and third solutions can transition between the 2 specified ellipses, but need to flip assembly branches in order to do so. The fourth solution contained a workspace that was very small due to a small link length and would not be usable. For the second example, we specified 2 ellipses at the same point in the configuration space, but with very different force-velocity properties. The first 2 solutions worked as expected. The second 2 solutions contained small link lengths, making them degenerate. For the third example, ellipses were specified with a flat aspect ratio. This is in order to offer superior force transmission characteristics in the vertical direction. The first solution worked with no problems. The latter 3 solutions can transition between specified ellipses, but are required to transition through assembly branches in order to do so. This paper presents a new way to synthesize multi-degree of freedom mechanisms according to ellipse constraints. The synthesis equations were formulated for a 5-bar linkage to pass through 2 specified velocity ellipses. The synthesis equations were solved, finding 4 solutions in closed form. We concluded by providing a few examples. Thank you.